Station 3 is geology of the area, and it's covered by Professor John LaChoy out of UW Green Bay. And the information covered will include the bedrock geology of northern Wisconsin and upper Michigan, the glacial history of Wisconsin, and the identification of the rocks present on the property.
My name is John LaChoy. I am a professor at UW Green Bay, and I've been there for about 19 years, and my specialty is a combination between sedimentary rocks and how water and rocks interact with each other. And you might be like, what the heck is that all about? Well, how many people have heard about Wisconsin having an arsenic problem or other issues with water? Those naturally occurring minerals that are in the rocks will dissolve or oxidize or change, and it affects the drinking water quality. And so that's part of what I study. I also study ancient ore deposits and other things, and I look at tiny little fluid inclusions inside minerals that are smaller than pollen grains, and others that are and other things I deal with are related to isotopes in minerals. Let's do this. Lots of other stuff. So my research and teaching ranges across the board for lots of different topics on water and geology. And did people get handouts yet? Maybe some. Okay. Yeah, maybe you could pass these around. Sure. So I put together a handout. The first time of the day we're getting a breeze here. Why don't I do this? I think that'll help a little bit. The geology of Wisconsin is pretty complicated. It varies from the north to the south a lot, both in the age and type of rock that we have, as well as the presence or absence of glacial materials and other kinds of resources and water availability and landscape slopes and styles and things like that. So the place I like to start is with a topographic map. This one's called Landscapes of Wisconsin, but you'll notice that the highest elevation areas shown in brown up here are kind of similar to what we have down here, except the patterns down here are very dendritic, right? Like a tree branch. They kind of like a oak tree or something. They branch out randomly. These are bedrock controlled hills and valleys where random stream drainage networks have cut into them, but these rocks are mostly horizontal. Over in this part of the state, the rocks are tilted, and so we get stripes on that bedrock geology map in the middle there that look a lot different. Plus, glaciers came over the east side of the state that did not impact this driftless area part of Wisconsin. The north up here is very different. We don't have those kinds of rocks at all. Instead, we have much older rocks preserved here with a large pile of glacial sediments. So the glacial sediments here in some places can get 200 or 300 feet deep across pretty wide areas. There are a few things that you might see that stand out, like this area here, or there at Rib Mountain, or the Baraboo Hills, or these ridges here, and a few others. Those in close by to where we are, Thunder Mountain, McCaslin Mountain, places like that. Those are different types of bedrock that are really resistant to erosion, and they stick up. Things like quartzite and other resistant rocks. So where are you all from in the state?
Near Green Bay.
Okay.
Wood County.
Wood County, okay.
Dane County.
Dane County, where was it?
Crivets area.
Crivets, okay. Where are you from, sir?
Well, Green Bay,
Oh,
but we have a place in Merritt County.
Okay.
Got two places. So.
Yeah, Dane County.
Dane, okay.
Marinette County.
Marinette?
Wood County.
Wood County,
Central
okay.
Sands.
First group of people from Wood County. That's interesting. Okay, so the geology in Wood County in Central Sands is very different than here, right? I mean, it's completely different. You're not going to see too many places with rock exposed like that at the surface. Instead, you've got an aquifer that's 100 to 300 feet deep, whether it's loose sand and gravel or sandstone, and while the sensitivity of the aquifer and the trout streams and things can be there if you lower the water table, almost an unlimited water supply in effect. totally different here. If you sink a well here, you might not get any water at all. You may have to dynamite or hydrofracture this rock or choose a different location to intercept a fracture, and you may only get a couple gallons a minute. That could be maybe enough to take a shower or flush the toilet, but not do both at the same time with laundry or something. So it depends. It really depends where you are. Most of the state has pretty good water supplies, but we're not here to talk too much about groundwater, although we can get in there if we want to. I want to start with this map. So you might have heard of the term bedrock, and as much as people probably have wanted to forget about the Flintstones, which is probably a good thing, it has nothing to do with the Flintstones. Bedrock is the solid connected rocks that underlay all of the sediments and soils. So if you could take a giant vacuum cleaner or pressure washer and just get rid of all the soils and all the trees, just kidding, and get rid of all that stuff, this is what you would see underneath it. So this is the bedrock. And there are other maps that show glacial sediments, like that map there. Soils maps, you might have heard of some of the USDA maps. There's Web Soil Survey is a great one if you want to look up your soil series to see what type of soil you have. Some soils are obviously more conducive for certain types of trees and other crops than other types of soils. Dry soils, wet soils, and so on. But this is the bedrock part of it. And you notice that there are very different color patterns on here. That's because in northern Wisconsin, these rocks represent very old, what are called Precambrian, igneous and metamorphic and other kinds of rocks. So that rock is a granite. And they're neat, but it's not a lot of variability where we are here. All along the roadside and where you're standing back there, it's all the same granite material. What we're looking at is the plumbing system of an ancient volcano. The volcano would have been higher, it's now uplifted and eroded away. And we're located right about here. On the handout that you all have, the red dot on the front page, the red circle, that's about where we're located. So we're in this pink granite, and it's about 1.83 billion years old granite. So it's part of this green stripe of volcanic material. And when Wisconsin formed or started forming around that period of time, there was a continent to the north, and this was an island arc, kind of like Japan. And an ocean basin was closing between them, and when they crunched together, they made a mountain belt called the Pinocchian Mountains. And so we have the roots of that mountain range exposed in northern Wisconsin today. And so we can see the minerals that are present, know that they form deep underground. We can do laboratory tests and stuff like that. And then for those of you in Wood County, this part of the marshfield terrain, we call it, was another block that hit. And later on there were others in south central Wisconsin and even Illinois as the continent grew by accreting smaller pieces together. So where are the mountains today? We don't have any. Each of these mountain building events made mountains, but it takes a couple 100 million years for mountain ranges to go away. If you look at the Rockies and the Appalachian Mountains, they look like big mountains, but both of those mountain ranges have been eroded flat a couple of times. They've just been bumped up other times. Even the Sierra Nevadas you all heard about Yosemite National Park? Half Dome? That's a granite just like this. It formed deep within the earth. It's the plumbing system of a volcano. The volcano's gone. It's been uplifted. And so you're just looking at the older rocks that are underneath. On top of these very old rocks, a lot later in Earth's history, about the rocks we have are 500 to 450 million years old. These are oceanic, mostly oceanic rocks like sandstone, a little bit of limestone, but it's mostly been changed to dolomite or dolostone, and some shale, which is a mud rock here. So southeastern Marinette County has some of these sandstones and dolomite rocks, and where you have those, they make great aquifers and plenty of water available. But the pHs of soils, how many people ever do any addition of lime or anything for changing pH of your soils? And where are you at again?
On central sand.
Central sand. So what is central sand made out of? Quartz.
Quartz.
And so it has no ability to buffer the pH. It's probably pretty acidic, especially with organic acids. So unlike these guys, which have all this carbonate material, over here and everywhere up here, blueberries love growing on acid soils, right? Like 4.5 for a pH. There's no carbonate rocks up here to naturally buffer that. So anybody who's doing agriculture up here that has crops that need higher pH systems, they've got to add all that lime to it. And central sands is kind of a little bit different because you're dealing with glacial sediments, but the same idea. Excuse me. So these rocks once existed across much of this area, and we can see remnants over here in Lincoln County. Irma Hill, if anybody's ever heard of Irma, on Highway J. That's a little piece of this sandstone that's still preserved. It's really well cemented together, and there are a few others too. But this sandstone is what's exposed in the Wisconsin Dells and up in Pictured Rocks National Lakeshore. It's where all the cities like Pulaski and Swamico and the backup wells that are still there in Green Bay, Fond du Lac, Waukesha, all those cities are pulling out of this sandstone aquifer that's deep down. And if you go under Lake Michigan, it's 3 miles underground in lower Michigan, and it's got, brine and oil and gas in it. So, totally different. But by the time you get over here, it's pretty salty. So people who have deep wells here, they have a lot of problems with high dissolved solids. So that's what forms kind of the bedrock part. What you all more likely interact with are the glacial sediments. So in places where the rock is hard and durable, it'll stick up. The highest and most resistant places are made of quartzite, which was sandstone smashed in a mountain building event, and it's just quartz. It doesn't dissolve. It doesn't abrade away. So Rib Mountain, Thunder Mountain near here, Castle Mountain, the Baraboo Hills, Barren Hills, those are all quartzite. But other places where the rock is pretty resistant like this, it'll stick up as mounds, and it gives people some challenges sometimes. But there's bedrock under all of the low areas too. We just don't see it. Unless you interact with it in a well, it might not be something that shows up. And it's usually a different composition, which is why it's not sticking up. This map shows something totally different. It has nothing to do with bedrock at all. It's just materials left behind either by the glaciers or by running water in river systems or in front of the glaciers. So there are a couple different colors on here. The brown indicates glacial till. And glacial till is material that's left behind directly by melting of glacial ice. And it can either be in large flat areas when the glacier melts quickly, that's called ground moraine, that's the lighter brown, or it can be a place where the glacier is feeding material and it's melting at the same rate that it's moving forward, so the end of the glacier looks like it's parked, but it just keeps feeding, and you get this ridge of material called a moraine. That's what these long brown ridges are. They're moraines. There have been lots of ice ages in Earth's history. We're currently in an ice age, and that's why we have glaciers in Antarctica and Greenland and things like that. But we're not at the peak of the ice age. We're in an interglacial. So North America and Europe aren't glaciated right now, and so we enjoy this nice warm weather. But there have probably been dozens of glaciations that have come into Wisconsin. We don't know how many. The old story was 4, but we now know from ocean drilling records that that's not accurate. We just can't see them. They've been eroded away or covered up or reconstituted in the next glacier advance as they come by. But what we do know is that in Wisconsin we have some glacial material, like over here in Marathon County, that's at least 780,000 years old. You guys know about magnetic polarity switch, where the compass will at some point switch and point to the South Pole? Have you ever heard about those things? Well, that happens episodically in Earth's history. The last time it happened and it switched to our North Pole compass setting was 780,000 years ago. But these glacial tills reflect preservation in the opposite. So we don't know how old they are. Can't carbon date them, because carbon dating is only useful for about 50,000 years.
How do they reflect that?
Tiny little particles of clay and iron, especially in deposits like lake sediments and others, they will orient themselves in the magnetic field before they get compacted. And then it's really tough to get that signal out of sediments, but you can take the core, orient it how it is, and then put it in a special magnetometer in a laboratory that's cooled by like liquid helium or something like that. And I saw this demonstrated once, and you can get a signal out, certainly for up or down polarity. Like in an igneous rock, it's super easy. You put it in, the thing spins, 10 seconds later you have your answer. And it's such a strong magnetic field. But people do that. There's some people, that's their expertise, and they do this in ocean sediments that they drill in the ocean rocks and all sorts of other things. But all we know is that these are really old. Some of these are a little bit younger. They might be older than 40,000, but they're pretty old. And the most recent glaciation we call the Wisconsin glaciation. People around the world call it that because some of the first ideas and concepts were noted here. You've probably heard of the Kettle Moraine, right? It's a famous place. People around the world know about that. And the Green Bay lobe, which is this lobe of ice, left behind this nice blob shape here. But there was one in Lake Michigan too. There was one here in the Langlade lobe, the Wisconsin Valley lobe, the Chippewa lobe, the Superior lobe, and many others across the northern tier of states and Canadian provinces. But before the Wisconsin Ice Age, which started 80,000 years ago and really got into Wisconsin about 30,000, was something called the Illinoisan glaciation. That was 150,000. And you can see down here south of Janesville and all the way to southern Illinois, the ice made it all the way down there. And so there's older glacial deposits there. But what we're likely to see in this part of the state, really eastern Wisconsin, is 3 different ice advances and basically the ice melting out of the state. So it advanced in about 30,000. It reached its peak about 20,000 years ago. And so here east of Antigo or in places like Coloma and areas, that ridge that you see is the terminal moraine, the end point of where the glaciers reached. And then they left the state in just a couple thousand years. So they came in, reached their peak, and then they were gone, re-advanced all the way south to this point right here at 15,500 years ago. Covered up some trees that we can age date and things like that. And then it left the state, and then it re-advanced again down to Appleton at 13,500 years ago. So ice came in, left, and came back in just 2,000 years. Could you imagine how dynamic that is? We think about glaciers in mountains, moving small distances and small volumes of ice. This was a lot of ice melting and growing, changing a lot at the end of the last ice age. And then by about 12,000 years ago, Wisconsin was ice-free. By about 10 or 11,000 years ago, Lake Superior region was ice-free. And then just some remnants up in Canada. And by about 6,000 or 7,000 years ago, all the major ice sheets like Europe and North America, they melted, and that's where sea level has stabilized since then, so we don't have much change. What we're looking at here in Athelstane, which is right about here, it's actually on the map, listed the word Athelstane. Not that it's anywhere near the biggest city around. I've never been to this city before, but I've known about it for nearly 35 or 40 years. Because glacial geologists call one of the moraine areas the Athelstane moraine. And on the back page, you'll see Athelstane in those words. So those black lines on the blue map, they indicate the positions of the glacial moraines. And Athelstane just happens to be one of them. So the more recent 13,000 year advance never made its way west as far as Athelstane. On that blue map, you'll see the little arrows, right? What are those, do you think?
Is that the movement of the ice sheet?
Yeah, that's the direction of ice flow. So how do we know that?
Striations in the rock?
Yeah, the striations in the rock. So when glaciers have rocks glued in the bottom of them that slides across the rock, it'll scratch. Sometimes it'll hop and skip, like dragging a chair with a little rubber feet across a tile floor. It'll go that because it sticks and releases and sticks. And when it does that in a boulder under the ice, it'll chatter away at the bedrock, leaving these special curved gouges, and they're cupped in the direction of ice flow, so we can get unique ice flow. Some parts of northeastern Wisconsin, the glaciers actually flowed to the northwest. And that's because glaciers flow just like rivers do, from high elevation to low elevation. And when the Green Bay lobe had to spread out, mostly it was going to the south, but it was also spreading east and west. Over here, it ran into the Lake Michigan lobe. And they bumped up against each other, did a bunch of weird things, and we call that the kettle moraine. That's basically what it is. Over in this area, it kind of flowed more to the west. So up in Stevenson, Michigan, in this area here, and a little bit in Marinette County, you can see drumlins, the linear ridges that you see if you drive kind of between here and Escanaba. All of those ridges where they farm the hills and the swampy fens are in between, those are drumlins with shallow groundwater. The same drumlin types exist down here, except the trees are only on the drumlins and they farm the flat land that's well drained in between. So it's kind of the opposite effect of where the trees are stable. A couple of other things you see, the bright yellows are the outwash. So the central sands region over here, that is very well sorted sands and gravels that are out in front of the glaciers. So the glaciers never actually made it here. But there's some other outwash that's in the glaciated terrain that's shown in orange. The blue sediment here represents lake sediment. Outwash here is well sorted sand and gravel because it's from running water. The boulders are left behind. The sands and gravels could be moved along, braided streams. And then the suspended silt and clay, they go farther into some place like down to the Mississippi River Delta or something, or into a stagnant area. This one was Glacial Lake, Wisconsin, dammed up at a time until it carved through the dells here. This is lake sediment. This is lake sediment dammed up by the superior lobe of ice. And this is Glacial Lake Oshkosh. And when the ice was here, it couldn't quite make its way over the connection in Portage to get into the Wisconsin River. So we had a lake dammed up here. And depending upon where the ice margin was, the size and shape and depth of Lake Oshkosh changed. And so when the ice was here, this is probably where the water was. When it was here, the water actually ponded along the edge of here. So this is the Peshtigo Brook, whatever it says there. Not Peshtigo River, it says Peshtigo Brook on this map. I don't know if it's a different thing or not, I'm not sure.
It is.
Oh, yeah.
It is, okay. But
It's a large one.
but so depending on where this ice was, the lowest elevation in northeast Wisconsin is Lake Michigan. So water flows down the Wolf and through the Fox and out here. So anytime you dam up that low point, all those fines, the sands and clays, are going to end up here. So if you try to grow potatoes in my garden in Green Bay, it doesn't work very well because it's just hard, like a brick. And actually mud cracks occur right away. It's about impossible. But over here in the central sands, it's great for growing displacive root crops, except it dries out right away, so you have to constantly water it, and that's where the central pivot irrigation comes into play there, and here in Antigo and a few other places. So the map of glacial sediments here really controls the kinds of drainage and the kind of soil types that you have, but it's ultimately the geologic history behind this is what's controlling these dramatic differences from place to place. So somebody could be 3 miles away and have a completely different type of soil on their property and different landscapes, all based upon what was going on geologically in the past. Before we look at the rocks over there, does anybody have any questions?
What about that earthquake that took place there in Lake Michigan? Is that something you'd be worried about, or is that common?
No, it's common but rare. Geologically common, but long distances of time between the events. So every few years we get little ones. Anybody ever see I don't have a lawn chair, I would have just knocked it over. There's a meme that went out that showed a lawn chair tipped over. I survived the Clintonville earthquake. Remember when they had some of those booms in Clintonville? There are lots of little pops and clicks that happen in the Earth's crust. When a 2.9 is very difficult to feel unless you have just the right setup. But there was one in Marinette County a few years ago that actually ruptured the ground surface where people were. I think that one is the one that I had a friend who operated the drawbridge in downtown Green Bay. He felt it and reported it because he closed the bridge for a while because his tower was swaying. They're sitting on top of this gooey mud that's 100 feet thick, and everything is kind of moving around. So, but a 2.9, It's not very big at all. There are lots of stresses that have been imparted by the glaciers here. Now the glacier's melting. There are stresses from the continent being squeezed. There are lots of faults. All of those black lines that are on here, that's only the giant major ancient faults. They're all inactive right now, but they can move just a little bit. Even in Green Bay area, there's faults that I've mapped. One of them goes kind of to the northwest, pretty close to the stadium, as best as I can map it. I wanted to call it Brett Favre's fault, but I didn't get permission for that.
Whose
so.
fault was it?
But there's some things like that, but I wouldn't really worry about it. You can get earthquake insurance for like $20 a year, but you're not going to be able to claim it. So you'd have to prove that it was from the earthquake.
You have to call you, right?
No, I mean it's probably not worth it. If we were to be impacted by an earthquake that was of serious consequence, and we could be, it would probably be from southeast Missouri or southern Illinois. The big earthquakes that occur there, they're magnitude 8, and they would definitely cause some damage to bridges that are not well seated in bedrock. I'll leave it at that. Like the Leo Krieger Bridge. But they're rare. The last time it's been like 1811 to 1812. I think there were 3 giant earthquakes. So they happen, but they cracked streets in Washington, D.C. and rang church bells in Boston. So that's where we would probably have to be concerned most. That or the Ohio to St. Lawrence Seaway. There's lots of earthquakes that can occur there too. But we're pretty far away from those.